Okay, in the last class we have discussed about the energy spectral density of energy signals. In the same context, you can define the power spectral density. So when you define the power of a signal xt, it is integration of minus t by 2 to t by 2 x square dt 1 by t limit t goes to infinity. This is how to define the power of a signal. Okay, that you know. Now, like we have defined in the energy signals that mode of x of f square is the energy spectral density, and if you integrate it from minus 2 plus infinity, you get the total energy of the signal. Okay. So likewise, we will try to represent the total power, the total average power of the signal in terms of the power spectral density. Okay. So to define the power spectral density, suppose you take a signal xt is of infinite duration, okay, and then you truncate it maybe between t by 2 to minus t by 2. This truncated signal I call it as xt of t, which is a finite duration signal definitely. And for this signal, of course, you will have a finite energy. And if you find the energy of this signal, that I say E of xt, that will be integral of x square t into dt, limits from minus t by 2 to t by 2. Okay, because the truncated signal exists only between minus t by 2 and t by 2. Beyond this, it is 0. So if you find the energy of the signal, of course, I integrate from minus 2 plus infinity, but ultimately the limits of integration will go from minus t by 2 to t by 2 x square d dt. And between this, between minus t by 2 and t by 2, your x t of t is same as x of t. Okay, so I have replaced this. Otherwise, it should be here x t of t, and that will be same as x square t dt. So this integral is basically, I can say, is the energy of the truncated function xt of t, which extends between minus t by 2 and t by 2. And in that case, I can write this p of x as limit t goes to infinity e of xt divided by t. Okay. So this describes the relation between the power and the energy of non-periodic signals. Okay. So you have the power px, which is given by limit t goes to infinity ext divided by t, where ext this is the energy of truncated function, energy of truncated signal. Okay, and for xt of t, if I find its Fourier transform and I call it as xt of f, then I can write the energy of this signal x of t in terms of its Fourier transform. That will be integral of mod of xt of f square into df. So this is the energy of the signal, and of course this becomes the energy spectral density, and this I can use here. So I can write the total power as limit t goes to infinity 1 over t integral of minus 2 plus infinity mod of xt of x square into df. Okay, or I can write it as integral limit t goes to infinity mod of xt square divided by t into df. So this gives me the total power, the total average power. Okay, and again I can define this quantity as the power spectral density, that is xs of f, which is limit t goes to infinity x t of f mod square divided by t. So this is called as the power spectral density. Okay, and the total average power is the area under this curve from minus to plus infinity. Okay, so using the same relationship what we have done for the aperiodic signals, you can find that the autocorrelation of this function and its Fourier, its power spectral density, they form a Fourier transform pair. Okay, definitely in this case the autocorrelation function will be defined in a different way, because we have to divide it with a t. Okay, when the signal is aperiodic, it is limited in time, then it is simply x of t into x of t plus tau d tau. So you shift this function with respect to itself by tau, and then you multiply and integrate. Okay, and since in this case periodic signals or non-periodic signals which are of infinite duration, you have to average this autocorrelation function over the entire time, right? Now this is for the deterministic signals. Okay, so if you have one signal or one sample function, you can find its power spectral density like this. Okay, so what you need to find is you have to truncate it between t by 2 and minus t by 2. You get a truncated signal, and then find the Fourier transform of this truncated signal, and then divide by t and take limits t equals infinity. That is how we get the PST. But when you have random process, now we will see how to find the power spectral density of a random process. Now in the random process, you don't have one sample function, rather you have a collection of sample functions. Okay, so if you have a collection or ensemble of the sample functions, then definitely when you define its power spectral density, so you have to find the average. So what you do basically is you find the PSD of this, find the PSD of this, find the power spectral density of all the deterministic functions that you have, and take their expected or mean value. That is how we get the average power spectral density of the random process. So I can say for a random process, your xf of f will be equal to, this is the same equation, limit t goes to infinity xt of f square divided by t, and then you have to find mean of this. Okay, where xtf is the truncated paths that we get from the xt between minus t by 2 and t by 2. Okay, and it makes sense because see, if you want to suppose apply some filtering to a random process, okay, so in that case you have to see the average power. So the filter must not be specific to this angular function or this because they can have their own power spectral densities. Okay, accordingly the filter frequency response will be different. But when you talk about the random process, you have no idea which sample function will occur. Okay, so any one of these can be generated, and then the filter that is designed to filter this random process, that should be based on the average of all these. Okay, so that is why we are taking the average of the power spectral density of all the sample functions that you have. Now we have to simply show that what is the random process, the autocorrelation and your power spectral density, they form a Fourier transform pair, and this already I have defined. It is your limit t goes to infinity as x t of f mod square divided by t, and you are taking the average value of all the spectral densities of all the ensembles or all the sample functions. They are simply finding its mean or average. That is what is called spectral density of the random process, and this becomes a Fourier transform pair with the autocorrelation function that we have to prove. Okay, now if you see this relation xs of f, which is limit t goes to infinity xt of f mod square by t, expectation of this, and if you find xt of f mod square, that I can write as xt of f into xt of minus f for real signal, and xt of f is the Fourier transform of the truncated pulse, truncated function, which extends from t by 2 to minus t by 2. So this I can write as integral of minus t by 2 to t by 2 x of t1 into e raised power j 2 pi f t1 into dt. This is for this, and similarly you have minus t by 2 to t by 2 x of t2 e raised power minus j 2 pi f t2 into dt2. This is dt. Okay, of course t1 and t2, these are the dummy variables, they will cancel in this integration, right? So you can use any variable, you can use any variable here, w, z, whatever you want, but we have kept these variables different because you have to multiply these two functions. Okay, and you have a double integration is going to happen. So this is the definition of the Fourier transform, and then I replaced your f with minus f, this minus j will become plus j here, that's it. Okay, and in fact you can combine these two as minus t by 2 to t by 2, another integral from, and then x t1 into x of t2. So these two exponential terms, they can be combined together, you will get minus j 2 pi f. What you will get inside is t2 minus t1 into dt1 and dt2. This is what is mod of xtf square. Okay, and I can use this relationship here, and this becomes limit t goes to infinity 1 by t, and this I will replace with this integration. So you have double integration. I'm not writing minus t by 2 to t by 2 again. Okay, so it is x of t1 into x of t2 e raised to power minus j 2 pi f t2 minus t1 into dt1 into dt2. Okay, and you can replace, and of course, yes, there is also a ensemble. Okay, there is the average value of this one, and you can replace this ensemble with the integration. Okay, so it becomes, because ensemble is also integration. Okay, so that will become limit t goes to infinity 1 by t. This is double integral from minus t by 2 by 2, and this I can write it as x of t1 into x of t2, mean value of this, into e raised to power minus j 2 pi f t2 minus t1 into dt1 into dt2. Okay, for this term, because it is a constant. Okay, so you are integrating with respect to a t2 minus t2 t1, it becomes a constant. Okay, so the mean of this will definitely be same, and accordingly I can write it as limit t goes to infinity 1 by t double integral, and if you look to this equation, this is nothing but or x of t2 minus t1. This is autocorrelation of the random process. Okay, at a lag of t2 minus t1 multiplied with e raised to power minus j 2 pi f into t2 minus t1 into dt1 dt2. Okay, and this is your x of f, which is the Gauss spectral density, and if you replace this, and if you denote this entire function with, suppose if I write it as phi of t2 minus t1, then I can write this integral as limit t goes to infinity 1 by t double integral over minus t by 2 to t by 2, and this will become phi of t2 minus t1 into dt1 into dt. Now if you look to this integral, now this is the double integral. It means it will basically give you the volume under the surface. Okay, if I take two variables, see, if I take two variables here, this is t1 and this is t2, then dt1 dt2 will become sort of a rectangular box. This is surface, and over this surface you have a function which is a function of t2 minus t1. So if you integrate this function over dt1 and dt2 with limits from minus t by 2 to t by 2, what you get is basically the volume under surface area, okay, over this region. Say this is t1 and this is t2, So if I say this is t by 2 and this is minus of t by 2, similarly this is t by 2 and this is minus t by 2. Okay. So the limits of integration are from minus t by 2 for t1 and then minus t by 2 to plus t by 2 for t2, and you have a function which is a function of t2 minus t1. So definitely when you integrate this function, the double integral of this function between minus t by 2 to t by 2 limit for t1 and minus t by 2 to t by 2 for t2, you will get the volume under the surface between this square region, okay, over the square region. So you have a, if you plot this t2 minus t1, this will be a function of tau, which is t2 minus t1. So you have a surface area basically. At which value of tau, which is t2 minus t1, you have some function value, and if you multiply this, if you integrate it, double integral of this, you will get the volume under this curve. Okay. Now this double integral can be converted into a single integral. So this integral simply means that you have a surface which is defined by phi of t2 minus t1, and the integration of this is nothing but the volume under this curve over this region, okay, over this square region. But you can convert this double integral into a single integral using the fact that your t2 minus t1 is tau, which is constant, because we are assuming that the process is stationary, so it depends only on the lag. So t2 minus t1 is constant, and so this t2 minus t1 is equal to tau, or I can write t2 is equal to t1 plus tau. It represents simply a straight line like this. Okay, so this is the equation of a straight line, y is equal to mx plus c, where this intercept is tau and the slope of the line is 1. So this angle is 45 degree. Okay, so this straight line represents t2 minus t1 is equal to tau, or t2 is equal to t1 plus tau. If I take another straight line parallel to this, which is t2 minus t1 is equal to tau plus delta tau. So this incremental difference is basically your delta tau. And if I find the volume under this strip, okay, we have a small strip here. As your delta t will approach to 0, in that case, this phi of t2 minus t1 will approach to phi of tau. Okay, so it will not be a function of then two variables, it is going to be a function of one variable only, tau. Okay, that is how you can convert this double integral into a single integral. And then what you simply have to find is the area under this strip. If you multiply that area with phi of tau, you will get the volume under this strip. And then if you define so many multiple strips, and if you find the volume under all these strips, and finally you add all the volumes, you will get the total volume under this square area. Okay, so to find this volume under this strip, what you need to find is that, I'll just draw it again. This is your t by 2, this is minus t by 2. So I have defined a straight line which is t2 minus t1 is equal to tau, which is constant. Similarly, this is your t by 2 to minus t by 2, and this is t1, this is t2. So when your tau will be equal to t, then exactly if I take this as, this is capital T2 minus t, and this is capital T2 minus t. When you take tau as t, then your straight line will be like this. It will be simply touching this edge. Okay, minus t2 plus t. Plus t is the y-intercept. So when plus t is the y-intercept, then your line will be simply touching this corner. For any values of tau which is less than t, it will be a straight line like this. Okay, it means in the single integral that you are converting, the limits of integration will be from minus t to plus t. Okay, because we have to include this entire square. So this entire square will come into picture when the tau will range from minus t to plus t. Okay, so what we are trying to do is we are trying to find the area of this strip. Okay, so you have taken an incremental difference which is delta tau, and as delta tau approaches to 0, you can take this phi 2t minus t1 as phi of tau. So you just have, we are just left with one variable. Okay, so the area of this will be like, I have to find the area of this. Okay, so in fact I have to find, I can approximate it with the area of this rectangle, because these two triangles that are left, their area is very small as delta t is approaching to 0, so you can just ignore it. And if you see this area, that comes out to be t minus tau into delta tau. Okay, and see how it comes t minus tau into delta tau, because this difference, you already know this is delta tau, this height. Okay, what I need to find is this distance. Similarly, if I take on this line, see on this line, your T2 is equal to T by 2, then definitely your T1 will be from this equation, it will be T by 2 minus tau. Okay, even if you take a point here, then this will be your T2 minus tau, because the T2 coordinate is T2, and your this coordinate will be T2 minus tau. Of course it will be a negative value. Okay, what I need to find is this distance. Okay, so this distance multiplied by this, I will get the area of this rectangle. Okay, so to find this, I will first find this distance. Okay, and at this point your T2 is equal to T by 2, and definitely your T1 at this time is T by 2 minus tau. Okay, so this much distance will be definitely, then it will be T by tau minus of minus T by tau, because this point is at minus T by tau. So what you get is basically T minus tau. Okay, now if this distance is T minus tau, and I suppose say there is some angle here theta, then this will become T minus tau divided by cos theta. Okay, this is a simple trigonometry. And similarly, I know this distance is delta t and this angle is theta. Okay, then this will become delta tau into cos of theta. Okay, so when you find the product to get the area, your cos theta gets cancelled. What you get is t minus tau into delta tau. So that is the area of this strip. So you can repeat this in the same process. You can have another strip by changing this tau between minus t to plus t, and if you add all these strips together, you will get the total surface area. So you multiply this, and over this strip your function is constant. Okay, because it is just a function of t2 minus t1, which is tau. So that is why how your double integration is being converted into single integration, and I can write in that case x of f as, and likewise this is for the positive area of tau. For the negative areas of tau you will get something like this, and you can say that for the negative values of tau it will become t plus tau into delta tau. Okay, so if you find the total volume, that will be limit t goes to infinity 1 by t. So that double integral will be converted into a single integral where tau will go from minus t to plus t, and you have phi of tau multiplied with t minus mod of tau into d tau. Okay, so you have, in one case you have t minus tau into delta tau, in the second case you have t plus tau into delta tau. So overall it will, we are taking it as t minus mod of tau into delta tau. So this will give the same volume whatever is given by this integral, but instead of using a double integration we are now converting this into a single integral. Okay, so you can take t common from this, and that t will get cancelled with this. So what we are left with, delta t approaches to infinity, integration of minus t by 2 to t by 2 phi of tau into 1 minus mod of tau divided by t into d tau. Okay, this is minus t by 2 to t by 2, and as your limit t approaches to infinity, this function will basically become 1. Okay, and if it becomes 1, what you are left with, integral of phi of tau d tau. Okay, and this phi of, so this you are computing xf of f, and this phi of tau you can replace this, it was rx of tau into e raised to power minus j 2 pi f tau to d tau. Okay, so this equation, if you see, it is nothing but the Fourier transform of this function, which is the autocorrelation function. Okay, so this again proves that your autocorrelation and the power spectral density, they forming Fourier transform pair. Okay,